12:15 appointment.
Oh, really? Okay, hi everyone, and welcome to this month's MAPP webinar. This is Dan Barry. Today's webinar is on the topic of high resolution and regional modeling, and we have 5 speakers today. We're going to hear first from Jim Kinter from COLA, the Center for Ocean Land Atmosphere Studies, and then from Jiming Jin from Utah State University, followed by Sarah Kapnick from Princeton University, Lucas Harris from NOAA GFDL, and Stefan Tulik from the Cooperative Institute for Research in Environmental Sciences. So Jim, are you on the phone line?
Yes, I'm here.
Okay, great. I'm going to switch control over to your computer now.
Okay. Okay, can you see that, Dan?
Yeah, it's still loading, but yeah, it looks good. So just go full screen, and whenever you're ready, go ahead and get started.
Okay, great. Well, thanks very much for inviting me to come and give a webinar. What I want to talk about today is results that have just appeared very recently in Bulletin of AMS on benefits and challenges of high spatial resolution in climate models. Just as a very quick motivation for this, the idea of improving fidelity of climate models is something we've been struggling with for a couple of decades now. And meanwhile, we know that numerical weather prediction has made significant progress in improving the fidelity of representation of the global atmosphere by taking advantage of the huge increase in computing power over the past 30 years, which is on the order of a million-fold increase in speed. In the NWP world, that has been done primarily by increasing spatial resolution in models, also improving understanding of physical processes, and importantly, also improving data assimilation methods. Well, climate models have also improved, but mostly because we've been focusing on processes that are important for climate rather than on spatial resolution or data assimilation. So what I'm going to talk about today is why we might want to look at enhancing spatial resolution in climate models to improve their fidelity. And the work I'll be describing started out several years ago after there was an event called the World Modeling Summit at European Center 2008. The outcome of that workshop was a call for dedicated petascale computing resources for climate simulation and prediction. And right after that meeting, the NSF had a windfall opportunity. There was a machine that was housed at Oak Ridge being operated by the University of Tennessee that was due to be decommissioned, and for a very moderate amount of money, they were able to keep the machine running. It was a machine called Athena. So they invited a number of groups to take advantage of that system. Ours was one. And so we called our project Project Athena just because that was the name of the computer. The project was a collaborative project involving a number of groups, including COLA, as well as European Center, JAMSTEC and University of Tokyo in Japan, and also importantly, the group that was actually running the machine, the National Institute for Computational Sciences at University of Tennessee, and their partner, which the vendor of the computer is Cray Research, or Cray Incorporated rather. We ran 2 different types of codes. One, a non-hydrostatic code. This is a global icosahedral model produced by the group in Japan. And we ran the NWP model, a global atmospheric model used for real-time operational prediction of the global atmosphere by European Center. Because we had a very large computing resources, amounted to over 70 million core hours that we consumed over a 6-month period, we were able to run a huge number of simulations with these models. In the case of the Japanese model, we ran a 7-kilometer global non-hydrostatic resolution version of that model for 8 years, all boreal summer cases. And in the case of the IFS, we were able to test the effect of spatial resolution. We didn't change model parameterization settings in any way, except those that are already scale dependent, like diffusion. But we ran a number of hindcasts, which were initialized with real global atmospheric initial conditions that we ran out to 11 months lead time with specified observed sea surface temperatures. We also ran long simulations, 47-year simulations, both with observed interannually varying SST globally and with projection of future 21st century sea surface temperatures, as well as a number of other experiments and ensembles to try to get at predictability and so on. So the project has, to date, resulted in a number of publications that are listed on the screen right now. And I'm just going to talk about a couple of the results that are in the papers that are highlighted with asterisks. So first, just to talk about how the model produces different sorts of large-scale atmospheric circulation. I'm focusing on blocking. I hope everybody on the line is familiar with blocking. It's this idea of very large excursions from zonal symmetry of the mid-tropospheric flow. So this is a map just showing a typical blocking event in the North Atlantic with a very large excursion of the flow and a big high-pressure system over the North Atlantic. Tebaldi and Molteni studied this, and many authors studied it. Tebaldi and Molteni invented an index that we could use to measure blocking frequency, and this is a depiction of that index as a function of longitude for a number of different simulations, all 47-year simulations with observed sea surface temperature, and then reanalysis. This is the ERA 40 reanalysis superimposed. The black line is the reanalysis, which is our target for this variable, and of course you see it peaking in the North Atlantic at about 0 degrees longitude, and also in the North Pacific at about 180 degrees longitude. I forgot to mention this is for the December through March season. And the grayish cloud around the black line is interannual variability of this index. So you see the blue line is our nominal climate model resolution, T159, which is about 125-kilometer grid spacing in the European Center model. And it's missing the maxima in both the North Atlantic and the North Pacific, falling outside of the range of variability of the observations. Whereas our T511, which is about a 35-kilometer grid, and the T1279, which is a 16-kilometer global grid, are both nailing the maxima in the Atlantic in particular. This is work that was done by Andrew Dawson and company, looking at these data in a little more detail, looking at the regime structures. And the top row you see are the four most frequent modes using this sort of cluster analysis that Dawson documents in his paper. He's labeled them with characteristic pattern names. So the top left is the NAO plus pattern. Then there's the BL pattern, the AR pattern, the NAO minus pattern. And then in the two rows below that, you see the depiction of these same cluster centroids. This is for geopotential height at 500 millibars, by the way. And you see those same centroids depicted for the nominal climate model resolution of 125-kilometer grid. And then on the bottom row, our nominal NWP resolution of 16-kilometer grid. And just by eyeball, you can see immediately that the 16-kilometer T1279 set of runs is a significantly better representation of this interannual variability, and in fact even the sub-seasonal variability of the structures, which is depicted by these centroids. The T159 has a facsimile of the same patterns, but without the same level of detail, without the same amplitude, and displaced in phase relative to the observed locations. The other thing I wanted to talk about, and you can sort of see from the list of sample results on this slide that there's a lot of other stuff I could have talked about, but for the time limitation. So I want to talk about tropical cyclones, which is not a typical thing we talk about in climate simulation. But here I'm showing results from Julia Manganello's paper where she's depicting the track densities in the North Atlantic for a 47-year period, or sorry, this is for a 29-year period, 1990 to 2008, for the May through November season. The map you see in the lower left is the observed value. This is from the best tracks, IB tracks data set. And what's depicted is the density of tracks for tropical cyclones in the North Atlantic. You see two large maxima, one in what's called the main development region, running along about 15 degrees north latitude from the west coast of Africa to the Caribbean. And you see another large value near the east coast of North America, just off the Carolinas. And I've drawn two lines on the observed value showing where the maximum values of these cyclone densities are occurring in nature. Then the other the other four maps you see there are different resolutions of these long simulations with the European Center NWP model, T159 to the right of the observed really misses both sets of maxima and has a kind of an amorphous blob of tropical cyclone densities in the central North Atlantic. As we go from right to left across the top row, we go to increasing resolution. You see better and better depiction of the maxima in both the main development region and off the coast of North America, implying that even with a hydrostatic model, we're getting better and better representation of the occurrence of tropical cyclones using the standard criteria that we use in these simulations. In this diagram, we're showing intensities as a histogram, and without going into detail because I don't really have time, the bottom line is that the higher the resolution, the better the representation of the peak intensities as well as the distribution of intensities for tropical cyclones. And I drew a line, an arrow there at the Northwest Pacific just to bring out the notion that, excuse me, the intensities that we see in the Northwest Pacific, most intense tropical cyclones of about a little more than 60 meters per second in the maximum surface wind speed, we see that being reproduced in the T1279 and T2047. I forgot to mention T2047 is actually a 10-kilometer global grid with hydrostatic dynamics. And you see T511 and T159 not able to produce those sorts of intensities. And the last thing I'll show about the tropical cyclones is what their structures look like. So here we're looking at the most intense tropical cyclones produced in simulations with these three different resolutions, the lowest resolution on the bottom, the 16-kilometer in the middle, and the 10-kilometer on the top. The two columns are 10-meter tangential wind velocities and total column liquid ice water. If you just look at the right set of pictures, which is the water content, you see again a sort of an amorphous blob in the T511 simulation that gets much better defined with a very good eye in the center and eye wall formation to the southeast of the center of the storm at 1279. And then in the 2047 simulation, we're even seeing multiple wall formation, and we see, we can't show it in this picture, but we also see cycling of that wall formation around the tropical cyclones. I'm going to skip this one in the interest of time and just go on to a summary. What we found in Project Athena is that by increasing spatial resolution, and these were just atmospheric component models, not looking at coupling, which is something that we're looking at now. By going to extreme spatial resolution, we improve many of the qualitative features of the large-scale simulation, which is good news. As expected, the things that are better represented the best are things that are sensitive to orography, which is better resolved at higher resolution, or geography, like coastal features. What was unexpected were some of the nonlinear impacts that we saw, particularly things like blocking and the tropical cyclone features that I showed today. They all improve with spatial resolution and possibly in different ways than we might have expected, looking particularly at, for example, those clusters of blocking events. And then finally, we noted that even because we didn't retune the model as we changed spatial resolution, a lot of the biases that are associated with physical parameterizations of things like tropical convection are still there. And in fact, they even get a little bit worse as we go to higher spatial resolution. So we still need to understand how to properly represent subgrid scale physics, which is a fundamental scientific challenge as we go to higher spatial resolutions. It's hard to get enough computer time to do the right level of testing and retuning that we need to do. The last thing I'm going to say before I quit is just to say, in addition to scientific challenges, as we go to higher resolution, we face a number of what I'll call logistical challenges. It's very hard to use a lot of computer time in research mode. It's also, there's this question I mentioned about resolution versus parameterization. Sampling to get to extreme events. There's a number of tensions that are listed on my slide I won't talk about. I just want to mention the one in red there that says exaflood of data. This term exaflood was coined a couple of years ago that people were worried about how we're going to deal with the huge amount of data that's flowing out of computers and satellites and so on, and people called it the exaflood. And for Athena, just this one project that we did over just a 6-month period, we generated over a petabyte of data, over half a petabyte of which is unique. So there's just basically one redundant copy of the data. And when we try to analyze that amount of data breaks everything. It breaks the computers we're using for analysis. It breaks our systems management policies. It breaks our networks. It breaks our software that we're using to analyze the data. And it makes it very difficult to share the data with other groups. So, you know, I see this project as kind of helping us see where the big problems lie in terms of understanding how to deal with big data. And what we did with Athena was all completely seat-of-the-pants ad hoc solutions. We do need to think about how we're going to know whether we've got all the science out of a petabyte of data. It's a number of publications already, and people are still working on these data sets. But do we know? Have we seen everything that we might be able to see? And Jennifer Adams, who works at COLA, said, well, we need extra-flood insurance. So I thought that was a really clever way to sort of phrase it in a short phrase that you might use as a take-home message. Excuse me. So I'm finished and happy to take questions later.
Great. Thanks so much, Jim. Are there any questions in the room here for Jim?
Yeah, if I might, Jim, Rick Rosen here. That was very good, as usual. I wanted to go back to your point about the challenge that you indicated in going to high resolution, because off the top of my head, I would have guessed that, or I thought the feeling was that as you go to high resolution, you might well start to eliminate some of those biases that exist in simulations, but that doesn't seem to be the case. Can you say a little bit, in fact, I think you mentioned in passing that in some cases those biases might be getting worse. Can you say a little more about that?
Yes. So it's actually the biases that we see do get smaller for things that we might be interested here in North America, for example. So the extratropical behavior of fronts and extratropical cyclones and blocking highs and convective weather in the summertime over the continents, those all get better, and the mean biases are reduced by going to higher spatial resolution. And I unfortunately, because of time constraint, I couldn't show you all those lovely pictures of how much better things are as we go to high resolution. The one that I'm pointing out about being a challenge, and the bias remains, is tropical precipitation. That one, you know, it's been the bugaboo for a couple of decades, and it's really completely a slave to the way that we're parameterizing tropical convection, which we still must do even at 16 kilometers grid spacing. We're not resolving clouds. We're not resolving convective complexes. So we have to parameterize convection. And what we chose to do for this experiment was not to retune, not to try to bang those biases back into place, as we might have done. You know, we could have used all 70 million hours just to do that, and then we would have been done with, we wouldn't have had any experiments to do. So, so the point there is that, yes, things do get, by and large, better, particularly outside the tropics, but there are big biases that remain, particularly in the tropics, particularly with respect to rainfall, which is primarily convective and is entirely parameterized. So we need to move beyond that to where we're not parameterizing the clouds, the convective clouds, or we have, you know, much better science to help us make scale-aware parameterizations. I know a lot of people are working on that. Scale-aware parameterizations of things like tropical convection.
Jim, thank you. That's very helpful. Thank you.
Yeah. I'd like to go to the phone line to see if we have a question. Before I do, anyone who's on the phone, please check and make sure your phone is muted unless you intend to ask a question.
Stu Weiss from California. I had a question about the resolution of atmospheric rivers. Taking a look and seeing how well those are being represented.
Okay, so the question broke up a little bit, but it sounded like you wanted to know how well atmospheric rivers are represented?
Yes.
Yeah, we're currently looking at that. The flow of moisture in the extratropics is extremely well represented in the mean, and a number of the extreme event behaviors that we've looked at, like extreme drought and floods over North America, those all improve with spatial resolution. As we go to higher resolution, they get better. We haven't done a comprehensive study. It's just a lot of data. to try to deal with. But we are looking at that, and I think so far the news that we have is
Jim, I think you might have broken up right there at the crux of the comment. Are you still on the line?
Yes, I'm still here.
Okay, what was the last word?
Might have been good. The news is good.
Okay, good. We're all relieved.
Thank you.
Are there any other questions either in the room and thanks, Stuart, for the question. Are there any other questions here in the room or on the phone line?
Yeah, this is Stefan Tulik. I guess dealing with exabytes of data, I mean, at some point you just have to have coarse graining algorithms embedded in your models and save data at resolutions that are coarse enough to process. And I mean, once you do that, then this problem of data, too much data, tends to go away, as long as you save statistics as well.
Yeah, that's right. And what we did for a lot of the analysis was we interpolated the output to the T159 grid for which we have ERA 40 reanalysis. So a lot of the large-scale atmospheric circulation statistics were compared to observations on the T159 grid. And that, as you say, that saves a lot of space. But you can't look at tropical cyclones on that grid, for example. And there's another paper I didn't talk about that Ari Solomon's been working on to look for tornadic environmental signatures. So looking at vertical shear and convective precipitation as surrogates for tornado potential. There again, you need that native grid, that 16-kilometer or finer resolution to pick up the features that are important. So, so I think it's a little of that we can get a lot out of a reduced grid, interpolating to a coarser grid to do a lot of the analysis. But still, if you're interested in things like changes in tropical cyclone intensity over 20th to 21st century, or changes in tornadic potential over North America, those we really cannot do with the T159 data. We had to go back to the original native grid from the model simulations.
Okay, great. Thanks, Stefan, for the question, and Jim, thanks so much for the presentation and answering all the questions. We're going to move on to the next speaker, which is Jiming Jin. Jiming, you on the line?
Yes, I'm on the line now.
Okay, great. So I'm switching control over to your computer now.
Okay.
So when you see the Share My Desktop button, just give that a click.
Okay, is that okay now? Can you see my slides?
No, not yet. So maybe try going to the Share menu on the top of your screen. Do you see that?
Okay.
And then click the
yeah.
My Desktop option.
Okay.
Okay, great.
Can you see that now?
Yeah, it looks good. Whenever you're ready.
Yeah. Yeah, today my topic is simulations lake processes and the effect on precipitation use a coupled Wolf lake model. So I introduced a little bit my collaborators. Hongping Gu is one of my group member, and Yihua Wu and Mike Eek is from EMC NCEP. So I give a simple outline for my talk today. First, I will introduce biases in the lake surface temperature reanalysis. Then I will talk about the coupling of the Wolf and a lake model. And then I will talk about the calibration and the validation of the coupled Wolf lake model. Then I will introduce the lake effect precipitation simulations. Last one, I give a little bit of summary. So objective of this study is to quantify lake processes and the effect on local and regional weather and climate is the weather research forecasting model. This model is developed by the National Center for Atmospheric Research. We recently coupled a physically based lake model to study lake effect snowstorms. This picture shows lake effect snow, so on the ground near a location near the Great Lakes. So first, I want to look at the difference between the non-lake surface temperature and modest lake surface temperature. Non represents North American regional analysis. Modest represents is moderate resolution image spectral radiometer satellite data. So from these two data, comparison of these two data, clearly see during the cold season, this is the cold season, we clearly see we have the NOAA data have a strong warm biases. During the warm season, the NOAA data shows a little bit cold biases. That's why, so the NOAA data is used for a lot of weather forecast and simulations. We will see how this data affect the lake effect precipitation in the Great Lakes region. This figure shows precipitation simulation at 10-kilometer resolution with WRF over the Great Lakes region. The top figure is for February 2006 observations. The red box you can see there is the precipitation pattern shows strong features of lake effect. The average of the precipitation over this box is 87 millimeters. But so when WRF forced with modest lake surface temperature, you see the average precipitation is 89 millimeters. It's very close to observed value. But when we force the WRF with LST, you see, some the precipitation the model generates stronger precipitation. This figure shows the realistic lake surface temperature is very important in simulating lake effect precipitation. So currently, all released versions of WRF model do not include the lake scheme. So lake surface temperature in these versions is provided by forcing data. So, so that's why we have coupled the lake model into the WRF. The model is originally developed by Hostetner. This is a one-dimensional water and energy balance model. The lake in the model is divided into 10 layers. So also we include ice fraction and the snow on the ice in the lake model. So we first applied to this model to Lake Erie. The average depth of Lake Erie is 19 meters with maximum depth of 64 meters. So in this figure, we can see the green stars is modest observations time series from September 2001 through November 2002. So dark line is buoy observations. This is buoy instrument here. So during winter time, this buoy station will be removed from the lake. That's why we don't have observations during winter time. The blue line here is generated by WRF lake model. So you see the model did a very good job in simulate lake surface temperature here. So for this shallow lake. But when we apply this model to the deep lake, like Lake Superior, the average depth is 147 meters with a maximum depth is 406 meters. You see the model generates strong biases. During winter time, they have more than 20-degree cold bias. During summertime, they have more than 20-degree warm bias. That's why, so this model may not capture some important processes, features of deep lakes. So through some modeling experiments, we found that for the shallow lake, the lake surface temperature is mostly controlled by atmospheric forcing. If you can generate good atmospheric forcing, you usually can generate good lake surface temperature simulations. But for the deep lake, besides atmospheric forcing, also deep water forcing plays a very important role in affecting lake surface temperature. We made a huge amount of sensitivity tests, to find out what causes the biases for those biases in the deep lake simulations. So eventually we find that the three model parameters are very important to deep lake simulations. So first one is AD diffusivity. Another one is roughness less. Also the bathymetry, and that means lake depth. So in the new calibrated model, we calibrate all these three parameters in the calibrated model. So we increased AD diffusivity by a factor of 100 and 100,000. Originally, it's too small, we find. We also reduced the roughness from 1 centimeter to 0.1 centimeter. So in original, the model states the leg depth at fixed values 50 meters. But in the new version, we use actually observed leg depth data to do our simulations. Afterwards, we use this calibrated model parameters. We rerun our model. We generate a red line here. You clearly see we have a huge improvement there. We capture the major time series of evolution of lake surface temperature over the season, over the entire season. Then we conduct multi-year simulations to validate our calibrated model. The first thing, so the first left figure shows biases in the NOAA data, NOAA data minus modest lake surface temperature. As we mentioned, there is strong warm bias here during winter time. This figure is averaged over the 2003 through 2008 or 5 winters. So you see over in the Great Lakes, so we see strong warm bias. The mean bias is 4.0 degree here. But when they use the Wolf Lake model to perform the simulation for the same period, we see the bias reduced to the 0.2 Celsius degree. We have a dramatically improved in simulating lake surface temperature here. Then I just mentioned this lake model also includes the ice fraction simulations. In this figure, left column represents observed ice fractions from satellite data, and mostly from satellite data. But left column is for model simulations with coupled Wolf Lake model. So for December, you see the spatial correlation between observed and data and the simulations is 0.55. So also we don't see much ice during the December. Also for January and February, so the spatial correlation can reach 0.82. So in this figure shows the model generates a very good spatial distribution of ice fraction over these 5 winters we just mentioned from 2003 through 2008. So also we perform, we simulate the lake effect of precipitation. The top row here is observation from University of Delaware. So for 3 winter months, averaged over these 5 winters here. The middle row represents model simulations. The bottom row is for WRF forced with lake surface temperature. You see from visual inspection, the model clearly have some improvement in lake effect of precipitation. In the red circles, we have see some lake effect features here. So clearly, so when compared to WRF force with NOAA data, so WRF force our coupled WRF lake model have some improvement. So this figure shows some bias, the domain average bias for precipitation. The blue bars is for WRF force with NOAA data, but the red bars is WRF lake, coupled WRF lake simulations. You see the average bias over the blue bar is 7.2 millimeters per month, but this bias is reduced to 4.3 millimeters per month. So with our coupled WRF lake model, outperforms RNS data in lake effect precipitation simulations. So I give a simple summary here. So of course, the coupled model realistic simulates the lake surface temperature and the lake ice fraction for the Great Lakes. Also, this coupled model reduced biases in lake effect precipitation simulations. So it's importantly, this coupled model has a capability of dynamic simulations of lake atmospheric interactions. So this project is supported by NOAA MAPP. Thanks. This is everything I have for today.
Jiming, that was great. Thanks so much for the talk. I'm going to open up the phone line, and I don't know if there are any questions here in the room or on the phone line.
Actually, I have a question, if I may, please.
Yeah, sure.
Yeah.
This is Cecile Penland. You showed 3 separate changes to your model, and I was wondering, were you able to decide which one was the most effective? There was eddy diffusivity, the roughness length, and the bathymetry.
Yeah, and most important was the eddy diffusivity. So the eddy diffusion, plays a very important role in the deep lake simulations. So that's why this one is the most important one. Introducing major bias. So the bias
then I have
yeah.
I'm sorry?
The bias originally is plus minus 20 degrees. When we improve, the bias reduced to plus minus 4 degrees, around 4 degrees. So the eddy diffusion is major improvement. Right.
I actually have a follow-up question, but ask other people if they have questions first.
Okay, yeah, sure. Are there any other questions on the phone line or in the room here? Okay, so Cecilia, you can go ahead with your follow-up question if you'd like.
Thank you. The follow-up question then is, if the eddy diffusivity was so important, what would happen if you gave a range of eddy diffusivities, like a distribution of them? Would that have an effect?
Yeah, what do you mean by distribution? Spatial distribution, or?
No, I mean temporal. If you let it be a rapidly varying random term with a specified statistics.
Yeah, that's important. So we also, this number, I didn't show the details how we parameter as the KE here. So this actually, the KE also is function of roughness and wind speed. Also, we put KE as function of time, season, and lake depth. So that's a different season, we have different KE. Yeah, that's not like the spring and the winter time. We have summertime. We have different KE. This is made. We tuning these parameters based on the temperature.
Okay, great. Cecile, thanks for the question, and Jiming, thank you for the presentation. Our next speaker is Sarah Kapnick. Sarah, are you on the line?
Yes, I am.
Okay, great. I'm going to transfer control over to your computer now.
Okay. That work?
Great. So whenever you're ready, go ahead.
Great. So I will be talking today about the importance of resolution for modeling global snow. And actually, a correction, my main affiliation is Princeton, but I also have an affiliation at GFDL, and so I'm going to go through looking at some GFDL model results for you today. Okay. So first question, why develop high-resolution global coupled models? 3 of the main reasons that I'm interested in looking at them is first, improving our understanding of the prediction intra-seasonal to multi-decadal variability. Number 2 is improving the prediction of transient climate change, especially with the role of the ocean in the climate system. As you increase resolution, we increase resolution of the ocean, and there's a hope that as you're increasing oceanic resolution, we might get some of the variability better and look at aspects of the climate system that really heavily rely on this. And number 3 is improving the prediction of changes in regional climate, hydrology, and extremes, with the third reason for looking at high-resolution models being what I will focus on today. So for this study that I'm going to show you, it's coming from a recent paper in Journal of Climate. We've used 2 main models, the GFDL CM 2.1 model and the GFDL CM 2.5 model. The CM 2.1 model has atmospheric resolution of 200 kilometers, versus the CM2.5 is much higher at 50-kilometer resolution. Our atmospheric levels have been increased from 24 in CM2.1 to 32 in CM2.5, and the oceanic resolution has also been increased from 100 kilometers globally to 28 kilometers at the equator to 8 to 11 kilometers at the high latitudes. To do these calculations of understanding changes in global snow, we've done two simulations. There's a control simulation of 280 years with 1990 fixed forcings, and there's another one which is an idealized climate change experiment that has 1% increase in CO2 annually until 2 times CO2 in year 70 and then constant thereafter. So first, going back to the original point of increasing these resolution in these global models is that you have improved, the hope that you have improved simulation in the ocean. So the top level is observations of 200 hectopascal December through February geopotential height, and these are the anomalies regressed onto NINO 3 SSTs. So you have this bipolar signal with the low off the coast of Western North America and the high over the northern interior continent. For CM2.1, which is the lower resolution model, we still have this low versus high, however, it's been shifted westward. These green dots are supposed to orient you to the original observed locations of this dipole. In CM2.5, we move this back, and actually the magnitude of these values has increased substantially. So CM2.5 is moving significantly closer to the observations versus CM2.1. So this is important for understanding differences in annual variability of snow, which I'm actually not going to show, but that's a case for future work. Looking now at precipitation over Europe, in Europe, the precipitation in CM2.1, you can see actually the resolution in the model from the large grid cell boxes. You have maximums over part of the Alps as well as the Scandinavia. However, as we go to CM2.5, when you increase the resolution, we're actually increasing the total magnitude of precipitation along, again, Scandinavia and the Alps, where the local maxima over Europe, which is significantly closer to what we see in the observations. So moving from the low resolution to the high resolution helps capture this maximum precipitation over these very narrow mountain range, high and narrow mountain ranges, compared to what we see in the original really low resolution model. So what does that mean then for snow? So this picture is depicting on the right-hand side mean annual maximum monthly snow water equivalent. So what this calculation is it's the total amount of snow on the ground, and at each grid cell we've taken the maximum amount over the 100 years of the control simulation that we have. So it's an annual measure of each grid cell what the maximum amount of snow that you have on the ground on average over the climatology. So on the right-hand side we have ERA interim reanalysis, which is 75-kilometer resolution, and the Canadian Meteorological Center reanalysis, which is, I believe, 24-kilometer resolution. So here, from both the reanalysis and the Canadian Meteorological Center data, you should have maximums, again, along the Scandinavian coast as well as over the Alps. If we actually then look at CM2.5 and CM2.1, you do get a maximum in CM2.5. However, we've overshot what we're seeing in the reanalysis products a bit, and you also get that same maximum over the Alps. In CM2.1, which is significantly lower resolution, you aren't getting that maximum over the entire Scandinavian mountains that you should. You just have one single point of maximum snowpack. And we actually completely don't even get any snowpack in the Alps. And the reason for this is that in CM2.1, the mountains are actually quite lower than in CM2.5 when we go to the high resolution. They don't even really reach 1,000 meters. Whereas if you look at the elevations in CM2.5, you're actually getting elevations above 2,000 meters in the Alps as well as in Scandinavia. And so we're getting we're capturing the orographic precipitation in CM 2.5, and the snowpack is, and it's actually cold enough, so you're actually getting this maximum snowpack in these regions, whereas in the low-resolution model, that isn't even evident. If we move to the Himalaya region, another region of interest for snow, we similarly get maximum snow over the entire Himalayan arc, as well as the two apexes of the arc that we see in the Canadian Meteorological Center. We don't actually get the interior Tibetan plateau snow that you see in the Canadian Meteorological Center, but we're actually getting the maximum snowpack and snowfall in this region that you should. ERA interim in this case actually has a known bias, negative bias, where it doesn't capture enough snow in this region. So we actually mainly compare the model results with this Canadian data. If you look at CM 2.1, again, you're actually getting maximum snowfall along the Himalayan arc. However, it's only in 5 grid points. So as a measure of understanding variability in snow over the Himalayas, looking in the model with resolution of 200 kilometers or lower actually won't really get you a full picture of what's happening with the snow, because you only have a few points that actually are capturing snowfall in this. I've also looked at the seasonal cycle of Northern Hemisphere snow cover. So this is the total area in the Northern Hemisphere that's covered by snow in a given month for the average climatologies of both CM 2.5, which is in red, CM 2.1, which is in blue, and then there's a Rutgers product on snow-covered area that has data from 1961 to present. So we've averaged the climatologies in the two models in the present climate versus the Rutgers product. And we find that they all have a very nice seasonal cycle with a minimum in August. And then as the snow begins to accumulate and you have increased snow-covered area over the Northern Hemisphere, we find actually that CM 2.5 really nicely captures this growth in snow-covered area during the accumulation season. Then when we reach January, February, however, CM 2.5 continues to have accumulation in grid cells, so the snow-covered area expands until March, whereas it actually starts to decline in the Rutgers product. So CM 2.5 captures the snow accumulation, the increase in snow-covered area very well in the early part of the season, but then we overshoot it. We believe that part of the reason that we're actually having this is our land surface model in CM 2.5 doesn't have an albedo that changes. So actually the snow falls and the albedo remains the same during the lifetime of the snow on the ground. I believe this has actually also been shown in WRF and other land surface model studies using NOAA and others, that if you actually change the albedo of the snow, you should have it melting earlier. So that's probably a likely cause of this bias. So CM 2.5 overshoots because of our albedo bias, but we actually get a very nice magnitude of snow-covered area for the Northern Hemisphere overall, compared to CM 2.1, where we have a nice seasonal cycle that follows that of the observations. However, we never get enough snow-covered area over the region, so we have a strong negative bias compared to observations in CM 2.5. These next few figures are going to actually show the differences in resolution for the signal in terms of climate change signal between the two models. So these are the transient spots. On the top we have temperature change, on the bottom we have precipitation change compared to the control simulation, with the dotted line representing when CO2 doubles. In both CM 2.5 and CM 2.1, temperature increases until doubling and then levels out, and precipitation also increases and level out. And in CM 2.5, we actually have temperature increasing at a greater amount and precipitation increasing at a greater amount than CM 2.1. If we look at snowfall, however, they both decrease significantly. And CM 2.5 actually decreases more than in CM 2.1, despite a greater increase in precipitation. If we again look at the seasonal cycle of snow-covered area, both models show a very similar reduction in total amount of snow-covered area through the season. You have about 5 million kilometers squared of change at the peak season of snow-covered area. So they have a similar amount, however, as a percentage-wise, it's a very different percentage. So if you're looking at these changes in these types of metrics in a lower resolution model, you'll have a greater percent decline in snow-covered area than if you had looking at the our higher resolution model. If we move to actual changes in total annual snowfall around the globe, we have this interesting signal where you have increases in snowfall in the polar regions in both the northern and southern hemisphere, and decreases outside of that, with a few locations which actually go against that rule. In the northern Yukon, right on the corner of Alaska and Canada, you actually have a very strong increase in snowfall. Also at another location in Alaska, you have a high increase in snowfall in the Karakoram region and some of the interior Tibetan Plateau, and you also have a strong increase over parts of the Andes. So these are a few unique locations that actually have increases in snowfall as a result of doubled CO2, despite that regionally at same locations along the same latitude, you have strong declines. If we look at these same locations in the lower resolution model in CM 2.1, these strong increases are actually lost. So you don't get the same strong increase in Yukon Territory in CM 2.1. You don't have the strong increase in parts of the Himalayan Karakoram, and you don't have the strong increase that we see in the Andes. So for all of these locations, what they have in common is they're actually extremely high mountains relative to the rest of the region. So in CM 2.5, you're actually resolving the heights of these elevations. This is actually Mount Logan, the Karakoram in this part of the Andes, where they're the highest mountains in the locations, whereas in CM 2.1, you're actually not resolving these high mountains. These mountains end up being less than 2,500 meters. So the cause of this is from the loss of topography when you're at lower resolutions. So 50 kilometers is the beginning resolution necessary to get these really high locations. And this isn't a direct comparison to what we're looking at, but this is historical data of snowfall on the left over Mount Logan, that same location that we see an increase in snowfall under double CO2. So over Mount Logan, you actually see that there's been an increase in snowfall since the 1700s. Similarly, over the Karakoram region, while most glaciers over the Himalayas are showing a decline in length, this one location actually in the Karakoram is actually seeing an increase in length. Now, glacier changes are not directly comparable to snowfall changes, since snowfall is one component of changes in glacier, but it does give some question as to whether maybe this model is capturing something in the double CO2 idealized experiment that we may actually be seeing in the present climate. So in summary, the present climate captures snow much better in the high-resolution model, particularly over regions of complex topography, and also in the northern hemisphere seasonal cycle of snow-covered area. With doubled CO2, you get very similar magnitudes of change in global snowfall and caused by global precipitation and temperatures. However, at certain really special high latitude and high altitude locations, you have extreme increases in snowfall. And this is caused, I didn't go into this because of time, but this is also caused by the precipitation signal in these regions overwhelming the influence of temperature. So in a few locations in the world, you will have increased snowfall due to increased precipitation. There are regions that are, in the present climate, are significantly below zero and continue to stay below zero, even under double CO2. So the important point of this is, with increased resolution, we actually have defined changes in snowfall over high elevation regions. So if we move from even greater resolution, from 50 kilometers to even greater resolution of the model, as those individual mountain ranges get smaller and in some cases get higher, we might actually see an expansion of these regional patterns where you have increased snowfall even under increased climate forcing. So thank you. I'm ready for any questions now or later.
Great, thanks a lot, Sarah. Are there any questions for Sarah?
Yeah, this is Anarita Mariotti. Hi, Sarah. I really enjoyed your presentation, very interesting. I have a question regarding your results where you show that the rate of increase in precipitation and temperature, changes when you, increases basically when you go from lower to higher resolution. Do we have an understanding of this result?
So yeah, part of this is we did move to more atmospheric levels and a slight difference in the radiation scheme, that might be part of the source of this. We've also only run one double CO2 run, so right now I'm running additional ensembles to calculate what the spread of this should be. So part of it is energetics in CM 2.1 versus 2.5, and I think that's the majority of the difference, but that's still a source of research.
Thank you.
Any other questions for Sarah? Okay, great. Thanks so much, Sarah. So our next speaker is Lucas Harris, who's actually in the room with Sarah. They're sharing the same computer. So whenever you're ready, Lucas, go ahead.
All right. So I'm going to be presenting some work on the nested grid climate simulations that I've been doing with the nested grid capability in our HIRAM model, our high-resolution atmosphere model. And in our global models, there's been a demand to better represent regional features at smaller and smaller resolutions. But to run at a uniformly high resolution over the entire globe is not always feasible given the current state of computer hardware. So what we like to do is we like to locally increase the resolution of our global model. And there's two ways to do this. One is to use a stretched grid, in which you take your coarse grid, your single grid, and you refine it so you get a higher resolution over your area of interest. And while this is conceptually straightforward, this is a bit of a one-size-fits-all approach in that your stretched grid is going to have a varying set of resolutions over it, but you're going to be stuck to one set of parameterization tunings for all those resolutions. And furthermore, your highest resolution region is going to dictate what your time step is going to be. If you instead use a two-way nesting, which is something that's very common in limited area models, but is very rarely used in global models, you have more flexibility to choose parameterizations that are appropriate for your high-resolution nested region, separate from those for your global model. And furthermore, you're not restricted. You can use different time steps in different other settings on the two grids as well. However, when you do two-way nesting, then you have to pay attention to how you're communicating between the two grids, how you're working with the boundary conditions of the nested grid, and how you're communicating information back to the coarse grid from the nested grid. So I'm going to be presenting some two-way nested results from our model. A brief description of the model we're using. So this is the HIRAM model, which is developed for efficient high-resolution climate simulation. We've been using this a lot in the model to resolve things such as tropical cyclones, tropical precipitation, and smaller scale effects in the mid-latitudes. This uses the finite volume dynamical core on the cube-sphere grid. All the results I'm going to be presenting today are going to be for the hydrostatic version of the model, but there is work under development to produce nested grid non-hydrostatic simulations. The parameterizations in this model are fairly sophisticated. In particular, we use this two-moment University of Washington unified shallow and deep convection scheme and a six-phase microphysical scheme. Two-way nesting is accomplished in a fairly straightforward manner. The boundary conditions are simply linearly interpolated from the data in the coarse grid into the boundaries of the nested grid, so nothing particularly fancy there. The two-way nesting is also fairly straightforward, but we still can remain mass conservative on the coarse grid simply by the fact that when we do our two-way nesting, our communication from the nested grid to the coarse grid, we only update the winds and the temperature. And in particular, we do not touch the air mass or tracer mass on the coarse grid, and if you don't alter them, they're going to remain trivially conserved. And since the other fields remain fairly well attached to the winds and temperature fields, not to mention the fact that doing two-way nesting is already mathematically over-specifying a problem, we believe that we should be able to get away with this without creating too much disruption onto the coarse grid, while still allowing the coarse grid to see the effect of the nested grid itself. So So the way that we develop the climate simulations is that we start by generating a good single grid simulation. We take a uniform resolution global model and we tune it to be able to get as good of a climate as we might be able to expect, a good global climate and good regional details. And then what we do is we do nested simulations in which we keep the global grid tunings constant, and then we tune the nested grid to see if we can't improve the regional details just by doing some tuning. And then the overarching question is that with the combination of increased resolution from the nested grid and the choice of parameterizations, can we improve the regional details over the nested regions compared to the single grid simulations? So two sets of simulations we're doing. You're using two different coarse grid resolutions, and in particular we have two control simulations, a single grid C90 simulation, which is a 1 degree model, and a C192 half degree model, which is the same resolution as the CM 2.5 model in the atmosphere. And these simulations have a 30-year AMIP varying SST, interannually varying SST simulations finished. We also compare that with a set of nested simulations. We nest at two resolutions. In the C90 1 degree simulations, we nest by a factor of 3, which gets us down to about 35-kilometer grid spacing. And in the C192 simulations, we nest by a factor of 2, which gets us down to about 25-kilometer grid spacing. We nest over two different locations. We nest over the maritime continent simply because that's the part of the globe that has the most effect on the larger scale circulation. And we also nest over North America simply because that's where we're most interested here at GFDL is taking a look at North American climate on local scales. We have a 30-year AMIP simulation complete for the C90 North American nested simulation. We do have some AMIP simulations for the other nested simulations are currently running. In their place, we have some preliminary 5-year climatological SST simulations that we can show to demonstrate some of the potential of the results. Now, to some degree, these are only prototype simulations, but eventually we want to push these down to higher resolutions so that our nested simulations can get to resolutions less than 10 kilometers, down to 9 hydrostatic spatial scales. So here are some results. This is annual average precipitation from our simulations and in particular the bottom 6 panels, those are all errors compared to the GPCP satellite data set. And you can certainly see some differences between the simulations. You take a look over the nested regions, say here for the maritime continent and here for the North American nested simulation compared with the two uniform resolution simulations up here. But the big thing is what you can't see here. And in particular, if you take a look at the nested simulations, you cannot see any clear artifacts due to the presence of the nested grids. You don't see any obvious artifacts due to the grid structure in these simulations, which shows us that at the very least we're not badly disrupting our global circulations by putting in a nested grid. We can zoom in and take a closer look at our precipitation statistic, or the annual precipitation on the nested grids themselves compared with the uniform resolution simulations. So here we're taking a look at the maritime continent nested grid and we're comparing this with a scaled TRIM precipitation data set. And with the TRIM data set, the biggest thing to look at is not necessarily absolute value precipitation, but the patterns of precipitation. So if you go from increasingly high resolution, so from the C90 simulation to the C192 simulation, about 50-kilometer grid spacing, to the C90 nested, about 35-kilometer, and the C192 nested, about 25-kilometer, you can see that you get increasingly good representations of the topography, not just over the Himalayas, but also you take a look to see you get better representation of the topographic precipitation on New Guinea Island. And this is a common thing we see when you go to higher resolution. They tend to represent the topography better, as Sarah also found. And as a result, we're able to get better estimates of orographic precipitation as well. Another thing you can see is that as you go to higher resolution, we tend to get less precipitation here in the Western Pacific, and we also get less of this wet bias here in the South China Sea as well. If you take a look at just the monsoon season, June, July, and August, what you can clearly see is that if you take a look at the nested grid simulations, we get less of this wet bias in the West Pacific than we do in the single grid simulations, the coarser simulations. And once again, you can also see that we get better representation of the topography in the wet seasons, both over New Guinea and over the Himalayas. One thing that isn't maybe not so great is that if you take a look at the nested grid simulations, that we do get more precipitation near the Bay of Bengal than you do in the single grid simulations, but it's shifted too far over over Burma rather than being over the Bay of Bengal like it should. Now, one thing you might ask is that whether improving our results, particularly in the Western Pacific, say, is due to having a better resolution over that region when we nest, or if it's just the fact that we have an extra set of tuning parameters, we can just turn the knobs we want until we get a better result. So what I've done here is I've done a separate simulation down in the lower right-hand corner, in which I've taken the nested grid simulation and I've replaced all the parameterization tunings with exactly the same they are on the coarse grid simulation here. And the big thing you can see, if you take a look at the Western Pacific, is that the nested grid simulations, even though these parameterizations are different, and this one, one of them is not necessarily appropriate tunings for this resolution, that they still look more similar to one another than does the single grid simulation. And we, in both cases, rectify this wet bias here in the Western Pacific. Although maybe this simulation is a little too dry, the coarse grid tuning simulation. So that implies that it's not just the fact that we get more parameterization tuning knobs to fiddle with when we nest. It's also the fact that we're improving our resolution that can help us improve our representation of precipitation structures, and not just in regions of topography either. So coming a little closer to home, here are the North American nested simulations, and here we're going to compare against this PRISM data set, which only covers the continental United States. But one thing you can see as you go to increasingly high resolution, we once again get a more realistic representation of orographic precipitation. And this is similar to what we saw again earlier over the Himalayas and New Guinea. One thing you can see is in the C192 simulation, we do get a little bit of overcatch here in the southeast. Longer simulations are starting to show that we are able to rectify this problem a bit. If you take a look out east, you can see that there's also differences between the nested and coarse grid simulations. And in particular, as you go to higher resolution, we're able to rectify this dry bias here in the C90 simulation as we go to a higher resolution. Once again, the highest resolution nested grid is maybe a little too wet. We still do have this problem with too much precipitation in the northeast in these simulations. If we go to the springtime, once again we see that the better resolution gets you better representation of the topography and orographic precipitation. And we're also able to once again rectify this moist bias here closer to the Gulf of Mexico. Not so much in the C192 nested simulation, but it does show up well in the North American nested simulation. We're also able to, at higher resolutions, rectify this wet bias up here in the Northeast. We do have a bit of a problem with too much precipitation on the Atlantic coast. If you go to the summertime, it's a little more disappointing. We don't see much of a rectification of this prominent dry bias over the Great Plains yet at these resolutions, even though we can go to increasingly high resolution. And we are still, once again, too wet on the in the Northeast. However, one thing we can do is that in this nested grid simulation, we are able to improve the precipitation bias, and we also see a little bit of that in the C192 simulation compared to the C90 simulation. We can improve this dry bias over Florida, and to some smaller extent along the Gulf Coast as well. One last thing I want to mention is the effect of two-way nesting. And now traditionally regional climate models are run that are independent of the global climate model that forces them. So essentially those are like a one-way nested model. And we have a two-way nested model here. How does using a two-way nest change the results here? So if we take a look especially at near the boundaries of the nested grid, we're seeing the entire nested grid in these cases. You can see that when you use a one-way nest, you get these clear artifacts near the boundary of the nested grid. In particular, you can see that this structure right here does not appear in any of the other simulations and is not in the observations. And so we can say that the one-way nested grid is giving you some artifacts that do not appear in the two-way nested grid. And this is even true, if we run out the two-way nested grid even longer, we still do not see any of these sorts of artifacts that we see in the one-way nested case. So we can, in this case, we can say that two-way nested grid is avoiding some of the problems that a one-way nested grid, a nested grid that does not feed back onto the coarse grid, onto the global grid, does. So in closing, we are able to show that when you increase resolution using nesting, we can improve our representation of orographic precipitation and some other precipitation systems as well, although not all the biases are alleviated by going to increasingly high resolution using nesting. So thank you.
Great. Thanks so much, Lucas. Are there any questions for Lucas?
Yeah, I have a question, Lucas. Hi, this is Anarita. I'm looking here at your last slide, the one that compares two-way versus one-way nesting and the results you find with this model. I'm wondering if you think this is a result that can be generalized to other models, or would it be specific of this model?
I think so. I actually did my thesis work on the difference between one-way and two-way nesting in a idealized context and found that one-way nesting tends to create larger reflections than does two-way nesting in some idealized context. And in the weather forecasting community, there's this general perception that's not necessarily been proven that two-way nesting does get you better results than does one-way nesting. So it's my understanding that we have a fairly good model already at that, and you compare one-way versus two-way nesting, that you should be able to see artifacts in the one-way nested case that you wouldn't necessarily see in a two-way nested case, particularly when you do climate simulations like this, where you're essentially averaging over a very long time period to see the same errors being made repeatedly in both cases.
Yeah, thanks.
Thank you.
A follow-up question I have is, I wonder whether you looked at the representation of the diurnal cycle and whether there is any impact with the nesting, and maybe, I don't know if 50-kilometer resolution is enough to see any changes.
I haven't taken a look at that. I'm not sure that your 25-kilometer resolution is necessarily enough to improve the seasonal cycle a lot, but I have not looked at it specifically in these simulations.
Are there any other questions on the phone? Okay, great. Well, thanks a lot, Lucas.
Thank you.
Our final speaker is Stefan Tulich. Stefan, you on the phone?
Yep, I'm here.
Great. Okay, so I'm going to try transferring control over to your computer.
Okay.
And yeah, just take a look and see if you can locate that Share My Desktop button. If you don't see that, you can go up to the Share menu at the top of your screen and then click the My Desktop option. There you go.
Am I sharing now?
Yes.
Okay, so I just want to start off by acknowledging my collaborators on this project, Julio Backmeister from NCAR, Bill Putman and Max Suarez from NASA, and Ming Zhao from NOAA GFDL. Okay, so with the computing resources we have today, climate simulations, at least atmosphere-only simulations with grid spacings of around 30 kilometers are now routine, and this is just an example of one model that's being developed at NOAA, which we've already heard about, the HIRAM model. And when you go down to these resolutions, one benefit is that you can start making more confident statements about how tropical cyclone activity will change in a changing climate. So that's one motivation for going to high resolution. However, if you look at these models in terms of their climate and variability, there's still a number of deficiencies, especially in the tropics. So just in the case of HIRAM, you tend to have too much rain at off-equatorial latitudes over the Pacific, and not enough rain over the maritime continent. And then if you look at the variability of rainfall in the tropics, you find that the model Kelvin waves are, so these are eastward moving Kelvin waves, are weaker than you see in observations, and there doesn't appear to be much of a MJO in this model. So what if you go to even higher resolution? The folks at NASA recently performed a 2-year run with the GEOS-5 model at 12-kilometer grid spacing, and this is comparing the Hofmahler of rain in the model versus the TRIM. And one thing you notice is, while it's getting the diurnal cycle, it's clearly overestimating the diurnal cycle. And the texture of the rain in general just doesn't seem to conform the observation. So I would say that the rain in the model is much more streamy and not as pointillistic as in the observations. And if you look at the variability in terms of the spectrum of rainfall, you find that this model still doesn't have an MJO. So to try and understand and mitigate some of these deficiencies in this project, we're using high-resolution global models together with expanded NOAA computing resources to perform 30-day hindcasts focusing on an MJO event. So rather than running long-term climate simulations, which is expensive in terms of trying to analyze the results and then make changes, we're doing shorter-term hindcasts focusing on the MJO. And in this project, we're looking at two types of models. The first is the traditional global model like I just described, where computing is being spent on resolving a continuous range of scales from the planetary down to the grid scale of around 25 kilometers. And then the other type of model is a super parameterized model where you spend computing resources mainly on resolving the convective scale at the expense of the intermediate mesoscale. So in the super parameterized model, what is done is you take a two-dimensional cloud resolving model and embed that inside each grid column of the global model. So this is just a list of the models involved. In terms of the traditional models, there's HIRAM at GFDL, GEOS-5 at NASA, and CAM-5 at NCAR. And these are all finite volume cube sphere dynamical cores. And then the super parameterized model that we're using is the WRF model. So this is a three-dimensional global WRF with as the large-scale model. And then inside each grid box of this 3D global WRF, I've embedded a two-dimensional version of WRF that's a cloud-resolving model. So this is a model that I've developed, and so if you haven't heard of it, that's why. And so the global WRF model uses finite differences with a lat-long core and its polar filtering. So the MJO event that we're looking at happened during 2009 between November and December. And this was during the Year of Tropical Convection Campaign, or YATC, and it's referred to as Case E by the YATC community. And this hub model is showing this event. So the raw field is, or the shading is the raw trim rainfall, and then these contours denote MJO filtered rainfall anomalies. So this is the event that we're focusing on, and I should point out that just by chance, this case is also the focus of a global model hindcast intercomparison project of the WCRP, WRRP, THORPEX MJO task force. So this, in the future, there will be an opportunity for comparing with the results from that work. So this slide just shows that this case is fairly representative of MJO events that happened during November, December, January. So the right panel is showing case E, and the left panel is showing a composite of strong events that happened during this period. And you can see that this case is fairly representative of the composite. This line here denotes a phase speed of 5.5 meters a second. Okay, so in all of the hindcasts that I'm going to be talking about today, the models are nudged to an operational analysis for a period of days to weeks to spin up the models, and then they're let go at a start date. And in the case of the traditional models, each of the models have grid spacings of 25 kilometers, and in each of the models, convection is handled partly through explicit dynamics. So you have grid scale updrafts interacting with diagnostic microphysics, and then partly by a standard convection scheme. And the partitioning between the explicit versus parameterized convection is model dependent. And then in the super parameterized WRF model, the typical grid spacing that I'm using is 2.8 degrees, so much coarser. And then the CRM grid spacing is 4 kilometers with 32 points. Okay, so first I'm going to look at some results for the traditional model. So this figure compares the observed versus simulated evolution of case E in terms of trim rainfall and European center 200 millibar zonal winds, averaged between 10 north and 10 south. And I've coarse grained the data to 2.5 degree resolution, just for ease of comparing all the models. So the first thing you notice is that at the start of the hindcast, this model captures this feature out in the Indian Ocean that lasts for around 10 days. And then in the observations, you start to see eastward propagation that it appears this model is trying to capture. However, there seems to be a fallout of rain in the vicinity of the maritime continent, and then you see a redevelopment of rain out in the Central Pacific. So broadly speaking, it looks like the model's doing something right. If you look at the GEOS-5 model, it appears that this model also captures this long-lived feature in the Indian Ocean. However, it splits it into two pieces. And then if you look out in the Central Pacific, it seems to capture this faster eastward moving envelope of convection. That's probably a Kelvin wave, but in this model it's too strong. And then later on it appears like it's trying to move convection eastward, but once again it seems like there's something going on with the maritime continent. And then for the CAM5 model, once again you see this feature in the Indian Ocean is captured, but then it seems that this simulation breaks down more rapidly, and you start to develop too much convection over the Central Pacific, and then nothing really seems to hold together after that. So if you compare the rain field in all these models, one thing you'll notice is that in the HIRAM model, it's much more what I would call pointillistic in comparison to both the GEOS-5 and the CAM5, which are much smoother. And so our hypothesis for why this is that in HIRAM, deep convection is being handled too much by grid scale updrafts versus parameterized updrafts. So in HIRAM, essentially the parameterization is a single strongly entraining bulk plume model, which is intended to mainly represent shallow convection. So in order for deep convection to develop, the model has to become sufficiently moist, and CAPE needs to build up so that convection can happen on the grid scale. So to alleviate this need for grid scale convection, Ming Zhao added a second, more weakly entraining bulk plume to the model to account for deep convection. And when you put that in the model, you see a significant change in the character of the rainfall. And now you're starting to, in this case, it looks like you're starting to capture this eastward propagation more accurately. And there's a significant improvement in the zonal winds. Okay, so now we're going to turn to the superparameterized model for further guidance. And the fundamental question I'm going to ask is, given explicit or 4-kilometer treatment of moist processes in a small 2D main, what aspects of the problem still remain? So for example, how do the results depend on the treatment of subgrid scale vertical mixing in the CRM, which is something that people don't usually talk about when they talk about cloud resolving modeling or think about. And then what about the horizontal resolution of the large scale model? Okay, so this panel is looking at the sensitivity of this model to the sub-representation of vertical mixing on the subgrid scale of the CRM. So the middle panel shows results where I'm using the MYNN 2.5 PBL scheme. And then the bottom panel is for results where I'm using a 3D Smagorinsky scheme. And sort of qualitatively speaking, this PBL scheme, this MIN PBL scheme, is more diffusive than the Smagorinsky scheme in the vertical. And so you can see that changing this vertical mixing has a pretty profound impact on the character of the simulation. So all the models capture this feature in the Indian Ocean fairly well, but then in both simulations, it tends to develop rainfall out in the Central Pacific too early. And then also in both models, you see this hole over the maritime continent region, so it seems like there's some issue with the maritime continent like we saw in the traditional models. And then if you look at this min case, you can see that rainfall tends to linger back here in the Indian Ocean, well, even though it shouldn't be, and then there's also all this enhanced rain out here. And so this widespread rainfall is sort of manifested in the zonal winds with this broad region of easterlies, whereas in both the observations and in this case, you have a much narrower region of easterlies. Okay, so now looking at sensitivity to the global model resolution, this panel is for the standard 2.8 degree resolution of the global model with 32, with the CRMs having 32 points with 4 kilometer grid spacing. And then this bottom panel is where the global model is 0.7 degree resolution, and the CRMs are 12 points instead of 32 points. So this run was 8 times more expensive than the middle panel. And one improvement that you see is that this heavy rain tends to develop later in the simulation over the Central Pacific, so that it's more accurately depicting this eastward progression of intense convection. And then you also start to see more rain developing over the maritime continent. So these two changes together give you a more accurate depiction of this this region of easterlies moving slowly eastward. Okay, so this is a summary of the lessons we've learned so far. Simulating the MJO using these traditional high-resolution models, the results depend crucially on how you partition the grid scale versus parameterized convection, and further tuning is still needed in these cases, but we have shown that you can make progress by adjusting this partitioning. And I think ultimately the parameterization should be doing most of the job based on the superparameterization results. So in the case of the superparameterization at 0.7 degree resolution, you're still fully parameterizing the convection. I think based on these results, past focus on convective closure assumptions as the key to simulating the MJO may be misguided. In the case of the SP run, I've shown that the parameterization of things like vertical turbulent mixing at low levels is also important, and this is actually consistent with other large domain CRM efforts like the Cascade effort in the UK and the NICAM effort by the Japanese. They've both found strong sensitivity to how vertical mixing is handled in these high-resolution models. And finally, the maritime continent barrier problem seems to be a serious issue in all of these models, and high resolution appears to be a necessary but not sufficient condition for improvement. So in the SP case, it seemed like we were mitigating this problem through going to high resolution, but in the case of the traditional models, there still seems to be a problem. That's all.
Great, thanks so much, Stefan. We have time for maybe 1, 2 questions. Are there any questions on the phone line or in the room for Stefan? Okay, well, thanks a lot, Stefan. Really appreciate your participation. I'd like to thank all 5 of the speakers today for their excellent talks. We're going to have another webinar in a month. It's on the first Tuesday in May. It's on the topic of intra-seasonal to interannual prediction, and we have 5 speakers for that webinar also, including Ben Kurtman from the University of Miami, Matt Newman from NOAA Israel, Dwayne Walliser from NASA JPL, Basu Misra from Florida State, and Kathy Pijon from NOAA Israel also. So thanks again to the speakers. Thank you, everyone, for joining, and I hope that you'll join again next month.
All right, thank you.
Thanks.
Thank you. Bye-bye.
Thanks.